Welcome back to Cloud Computing and Big Data, our course today in lecture 1. And this will be a lecture where we, have still relatively an overview of the whole course, but instead of, clarifying assignments and course content in different, let's say, individual lectures already that we did in the last time in the prologue, this will be really going already in some technology aspects like GPUs versus CPUs, what it is about this interesting term big data. Is it about volume or is there other ingredients that coined this term big data? So this will be all materialized during our lecture 1 today. But before we dive into the material of this lecture, let us review what we had the last time in lecture 0, which was a prologue. And you will see throughout the course that I always will give a review of the last lecture that we had. And this is usually a quite nice executive summary if you want. So what are really the key essence elements that you had in all of the different lectures? So in lecture 0, which was really just the warm up of the course, prologue, a general understanding what to expect in the course, we learned a little bit how these different terms really interact with each other, which sort of also motivates the course, right? Particularly when you think about this parallel and scalable machine learning. So we see here on this graph that we had the last time, we have really the data set volume, which is ever increasing with measurement devices that we also will learn today, to something we call big data. And there has been lots of, let's say, general purpose AI models in the past, which are not deep learning, but random forest, support vector machines. And they do a really good job. If your data volume is, let's say, adequate, and if your, let's say, your computing is enough for that. But if you go in the realm of big data, you will find that many of the serial tools we were using with these, like scikit-learn, R, MATLAB, and so on, have a problem on your laptop to work really. And the key essence to take away is really then this is the idea where you then have to move to a remote computing paradigm, let it be cloud computing or high performance computing, could be also. So they're basically standing for similar elements in terms of machine learning and deep learning. Cloud computing in this course means we have a much more, let's say, seamless way of getting to computing resources because we have lots of services. And these services will be also throughout the course coming from, typical cloud vendors like Amazon, Google Cloud, Microsoft Azure, and even scientific one like EOS. And the other aspect we had to learn really about this, and this is also now something that you already learned, I think from the media, the new hype on AI with large deep learning models, large language models. This is all of the realm that you see here on the top. So for this to work, you not only need, let's say, big data, because this accuracy that you see here, that the large deep learning networks like large language models and so on that you know from the media, you not also training time and a big footprint of computing to train them. So hence this kind of footprint here, this red thing means the better the neural network model, or let's say the bigger, the bolder, which gives us today cutting edge performance, right? That's what we're after, model performance, accuracy. That's what we want to achieve. So, but here you have to pay the price if you want, and you have to really use cloud computing and high performance computing. You cannot use these models just on a little laptop anymore. Maybe for inference, that's a different story. So you don't have to train it. Basically, if someone already trained it and you just use it, you know that from ChatGPT and so on, that's a different story. Then you do inference and so on. We come to this all over the course. There's several terms that, of course, you cannot know in detail. Lecture 2 will continue, for instance, with a machine learning introduction, where we will then also talk about training versus inference and all of that. Another element that I wanted to bring to your mind as a course motivation is really the flexibility we have today in creating new tools, new software. And this is basically the ingredient of these 3 factors, right? That really coined, or basically were the success of cloud computing, if you want, in the last 10 years, really scaling up. And we will have the term scalability again today when it comes to big data. So more and more large data sets will be available. We have examples today in lecture 1. But also the cost of it is less and less. That means we can store more, we can provide it openly for free. And these are all new ingredients to new startups, new SMEs, really working with this data to do new ideas with machine learning and deep learning by opening up data like high value data sets, for instance, we have in, public sector organizations like Statistics Iceland. Now, another element is the hardware, right? So many of you know and you remember from the last course, I hope, that GPUs were 20 years ago not in a HPC system, not in a cloud system, because it was for gaming, right? Gaming computers. Now we have this general purpose GPUs really fueling computing by orders of magnitudes of scale. And you see this training time here again to make the connection is really fueled by GPUs these days. So there's not only NVIDIA, there's also AMD GPUs these days. But the hardware, let's say, technology evolution was really key ingredient as well, why machine learning and deep learning in cloud computing is these days really on vogue. And finally, let's not forget open source software. A large movement in the last 10 years again, more and more tools are open source, known fellows like TensorFlow, PyTorch, Keras, you name it. These are all publicly available. So, when I started in that, we had to develop our parallel SVM on our own. There was just no tool on it, right? So we basically have created it on our own on neural networks. We started with some master seeders, for instance, implementing parallel neural networks 15 years ago. Now, this is all brilliantly implemented, I have to say, in PyTorch, TensorFlow, and also with high performance, leveraging the hardware and being able to scale on big data. And with this, all these three key ingredients, we see more and more breakthroughs in science, engineering, but also new businesses evolving and new facets maybe also on this learning strategy that you have seen again with ChatGPT. And so generative AI modeling, right, is also fueled by these three factors. Now, then the other part of the prologue was the course organization and content. That is sort of the idea what to expect in all over the course. Everything will be managed via Canvas, in certain cases via UGLA, but Canvas is really where we notify you about special IHPC workshops that were coming, and thanks for all of you that participated, but also, say something about the lectures when we have our course hours and so on. And of course, most notably also to the industry project, which is 50% of the course. Throughout this, let's say, journey in the course, we will have not only this deep learning packages and so on. So of course, we also have general services that we will look at, but we have always a special, let's say, emphasis on this machine learning and deep learning or data analytics, which you see a little bit here, big data analytics driven by Apache Spark or Hadoop will be also part of the course. Coming back to high throughput computing approaches, divide and conquer approaches, and of course, many things are fueled with Python and Jupyter notebooks, as you will explore, especially in the practicals. Now let's come to the lecture today. So again, it's more or less an introduction, but on a different sort that you had in the prologue, which was giving you much more course overview. Here we try to connect already the different lectures. I will give lots of pointers already to some of the lectures that will follow all over the course to make the connection really where are all these topics somehow combined. So you see, it's more or less, again, a conceptual topic, but it links nicely to many of the practical topics we will see and get you a better understanding of cloud computing as a whole. Now, the outline today then is really going to the foundations of cloud computing, understand why parallel distributed computing is so essential in this, and what does it really mean to have internet cloud systems. So, browsers, we can have nice services, accessed, but underlying is a lot of technology. And this technology advances we will talk about enabling parallel computing at scale, so that it also scales up not only to, let's say, one big large language model that you want to train, also to many different users, right? We will talk about this, that is a multi-user environment. The services are used worldwide, perhaps in Amazon, by thousands of users. So how do you scale up will be another technology endpoint we will talk about, and how this is fueled with, let's say, technology foundations that you really need to know by heart. So the difference between a multi-core CPU and a many-core GPU, for instance, should be something you really get out of this course topic today, as well as the idea of having a as-a-service approach with examples, while we, of course, if you remember the outline, have later also several different lectures on it, right? Where we talk about infrastructure as a service, platform as a service, software as a service. So these are key ingredients, really, where lots of these cloud vendors have services. The second part will be then shifting the focus a bit to the second emphasis of the course, a big data aspect. So what it is, why it is termed like this, what is the challenges when you work with, let's say, machine learning, deep learning with big data. Then we come to several limitations quickly, not only in terms of storage and storing everything what we maybe need to store today, but also the problem of the, let's say, throughput between disk storage and memory. And then we will also explore quickly how clouds try to solve it, have scalability approaches, have bucket stores and things you maybe already know from your MP3 collection. You have already maybe somewhere uploaded in the cloud, or today probably many people use just the service Spotify. Hence, we will talk a lot of these ideas, how now cloud's getting scalable again, making really connections to different materials in the course. Lots of these things are really fundamentals, and also here and less shaping again terminologies, like for instance big data analytics, and what is machine learning, deep learning in clouds, what technologies can help, and so on. So let's start by the foundations of cloud computing. This is all fueled by large data centers, and this is not obvious to you. We will see how that materializes in lecture 4. Actually, there will be a complete lecture on data centers, how they look on, and also, as I promised in the prologue, every year we usually go to one of the data centers here in Iceland. With the course, we will visit basically one center and also touch metal, as we would say, really look at all the racks, how a data center operates, and where you can have also questions and so on. And we'll also see that this is a large amount of infrastructure parts where virtualized resources are there that you can access remotely, right? This is, of course, a key element in the course, and in cloud computing. You have your laptop, that is, you have Bravely at home or here in the course. And whenever you use a cloud, you would have some request to it, shaping this interesting name cloud, right? So it's dynamic, and we will see how that materializes when we, for instance, add more storage or remove some storage, add some computing hardware or remove some computing hardware. Usually this costs, right? You will see I will always in the course work connections and make examples to, of course, the costs that you have in Amazon Web Services, MS Azure, Google Cloud, when you use these services, which is, of course, a business model, right? But the service character is really important. And another thing that is really important in this is the sort of idea that you really can easily access it with the web browser, with all these different services, and that you can basically bind these services together on the infrastructure as a service layer, connecting it to platform as a service layer components, and then, create a software as a service layer approach. For all of that to work, virtualization is a very important term. This is now in 101 computer science, so many of you should know already about virtualization, but we will also pick it up again in lecture 4, and we'll also show you why this is basically, the case that virtualization fuels so many aspects of this. And this is a bit out of sync, because normally we would have continued with this lecture 4 already in lecture 2, but to give the assignments early out, we had, feedback from students. It would be nice to start earlier with the machine learning elements and a little bit on Apache Spark and clouds before we can come back to some of the fundamentals in data centers. So when you think now about cloud computing, it looks like it has been always there, but there was a lot of evolutions in the past that really fueled it in parallel and distributed computing, really complicated technology around on high performance computing, as we call, where you have basically the idea of the difference that high performance computing usually stands for these large supercomputers, which are really having, a very good interconnect between the different nodes, while high throughput computing usually, you see here a little bit of boxes, smaller computing entities that have not really a very good interconnect. Both paradigms we will see remain throughout the course, and essentially are paradigms given that name. So you cannot exchange the one with the other, right? Otherwise, it doesn't make sense. So high throughput computing is another goal that high performance computing has, and we will also see the applications. Here in the course, we perhaps a little bit more oriented on HTC every now and then, although we also use some HPC techniques, especially when we train deep learning networks, because elements like Horowat that are then doing, distributed deep learning also rely on some of the HPC and MPI techniques. Things we teach rather in the other HPC course, but some of it will be coming back here. So hence, instead of using, a very big computer only in the cloud, the data centers are all connected, and the data centers are really fueled by different, let's say, sort of entities. And with this giving you access to basically these paradigms you have heard, now HPC and high throughput computing. Again, it's often HTC, but however, the underlying techniques like using GPUs at scale and so on are often also really high performance computing techniques. And again, the difference is very nicely visualized here. HPC is mostly characterized by having a very good interconnect between the nodes, while rather HTC uses, in the past, maybe commodity PCs or so. We will learn about this a bit about Boeing and so on, where at least the idea is that the network connection is not so important. You solve the task individually and then combine maybe the results. When we see this in a bigger picture, and again, we come back to this in lecture 4, there's really this convergence in a way where you say internet clouds have been, let's say, formed by more and more convergence of this technology. There was always a world of HPC, very costly systems where the interconnect is very expensive, and then you have clusters and so on that really had done, lots of scientific computing in the past, less maybe on industry or some industry engineering application perhaps, while the HTC systems have been a long time around for P2P networks, distributed computing in a very much more high throughput computing fashion. So really data analysis at scale or data analytics at scale. And by bringing them together to something which was coined computational grids, right? So grid computing, there was sort of a convergence more or less of these two systems by really connecting them together and, building these cloud-like things that you see already emerging here, right? Very dynamic. So depending on the user needs, a service-oriented architecture can give you many things. You just swipe your credit card and you get maybe a small HPC cluster in the cloud. A couple of GPUs you need. You swipe your credit card, and you have an Apache Spark, which is usually more rather on HTC with MapReduce techniques. So in the end, and then of course, let's say the internet itself evolved, right? With Web 2.0, internet clouds, Internet of Things, even have more and more measurement devices, sensors. This now from Philips, basically, right? From your light that you can steer with a simple app at home while you're not even there. So lots of these movements together coined in a way now what we have, the clouds, and that which was not so obvious 20 years ago when I started in the field, right? So the systems to use, you see here, the yellow ones, HPC, HC systems, were relatively hard to use. Setting up a MapReduce cluster was very hard, lots of different configurations. Using HPC systems, batch systems, scripts, and lots of interesting, libraries is also not the simplest. But the idea of the internet cloud is then really to abstract from all of that and make it much more easier for services. And hence, this was also coining now the big jump into the industry world, because it has to be simple when people pay for it, right? Scientists maybe work on a job script for 2-3 hours, still loving that subject, while users that swipe the credit card can expect a high level of service quality, and hence the service needs to be simple. Good examples you see here all over the place, where I believe the most of you or some of you have even used, I guess, the Google Cloud for your Google Docs document. Some of you may be even in Facebook, if not all of you, and Amazon Web Services. Chances are that you have at least used S3 somehow, a storage interface that we will also cover in the course. I will not go into the detail of all of them. We actually pick many of those all over the course. And there are some of them very specialized, while some of them are very general, and we come to this. But this is really the idea that fuels, the internet today. Many of the, let's say, service offerings we had in the past are now cloudified or in the cloud, and we make the case for it all over the course. Then more on terminology, that you really see the differences, and a little bit the ideas of the terminology, because they need to be understood when you have cloud computing, even on a 10,000 feet perspective. So when you think about a centralized computing service or computing entity, you would see, basically one big physical system. It would be rather a HPC system standing in one data center somewhere, and that's it. Right? So, and many of the data centers and supercomputers are centralized systems, but the cloud vendors connect them in different data centers. We will see this in Amazon, where you can even pick the region, the location, which data centers, where you want to have the services hosted. So cloud computing is larger than this. It's not centralized computing, talk about one big HPC system. That is just rather something we do in the HPC course, where we use, one big large supercomputer, which has 1,000 GPUs. And the trend there is even moving to modular supercomputing, right? So you see that a little bit with a deep project space here, a cluster module. So these are lots of CPUs for high single thread performance, number crunching, while here an extreme scale booster is fueled with lots of GPUs. So let's say moderate performance of the processors, but then many of them. Hence, we talk then also very soon about many core and multi-core. And then data analytics modules need lots of memories. We'll come to this with the difference between Apache Hadoop, Apache Spark, why memory is an important part. And then you can imagine service and storage plays a better role. This is extended these days, even with concepts of quantum computing, something we don't cover in the course here, but a little bit in the HPC course, so that there are new models on, quantum computing that we use, for instance, already in publications and in our research for optimizing machine learning. So quantum machine learning is already an application in quantum computing we actually use in quantum annealers. But let's go back to the cloud computing course here. But you see, both of these courses are a little bit connected. They talk about similar technologies, and hence parallel computing has fueled both, right? So parallel computing can be on different scales. So if you use it tightly coupled using shared memory, really writing, into the same shared address space, or you have distributed memory and you do message passing between them. These are all topics that are actually, again, more in HPC covered. But many of the algorithms we will see in deep learning, for instance, are in a way parallelized with this. So you will see, for instance, as I mentioned, Horowat is one technology for, let's say, scaling up deep learning really with multiple GPUs. We call this distributed deep learning, and we will learn this in the course. Then you need the message passing. You have to exchange the gradients. The gradients is the learning of deep learning models, and we come to that over time. But this is still an important technology. And to let's say, to see the difference to distributed computing, then you would say rather it's parallel computing across computers, right? The analogy you see here from the computational grid, and then coined a little bit also the cloud computing these days, and also more and more Internet of Things with more and more measurement devices coming in, and basically fueling also cloud services. This is something where we leave the idea of one data center. We have multiple data centers connected. Many of them have maybe different services, and we even connect to these, let's say, via the internet today also, these measurement devices I talked about. And this is, of course, really something that applied to all the cloud computing vendors. They do parallel computing, they do distributed computing at scale, really, like we'll also see in the AWS and MS Azure and Google Cloud. So the early examples of this, just to give you also in history on this, this was a little bit before cloud computing existed, where the Boeing idea, example for research here, which also helped in COVID-19, but the idea of Boeing was really to have, let's say, idle computers, right? You have these computers maybe here in Iceland, somewhere in a faculty, then in our Jülich Supercomputing Center, someone has a desktop computer running a long time and doing nothing. So this kind of resources that were unused, this is something where people have said, well, that's a tragedy. While people are not using it, let's bring them together. And this free unused computing power can at least help a little bit with some, elements that we use in science. And there were lots of them, basically building on the Boeing infrastructure really in terms of, which kind of different science problem you want to solve. We see here the example that, COVID-19 outbreak was used with this Boeing. So it's still on vogue, it's still used, a term that we call CPU scavenging, right? So basically that means this free unused computing power This is a little bit, let's say, in controversy more and more, especially if you think about now you need large-scale GPUs for many things, because largely you would say that the energy for running them here idle and so on, usually there are new techniques to really getting them, let's say, deactivated or maybe, shutting them off until they're not used because of the energy. Hence, this is a more older topic, but it fuels the idea where then cloud computing came from in the past before it existed. And then one of the first really key services that you could say count in the naming of this computing cloud, which is the elasticity, right? The elastic computing cloud, the EC2 services that have been coming from Amazon very early. While Amazon, many of you know as a bookstore, they had already a very fantastic cloud infrastructure underneath, which they also gave out for computing needs. So this is an interesting approach where directly, you again, as a customer somewhere, want to access some remote, computing power, but sometimes you would say it's enough to have, let's say, one rack. But many times you have something what we call maybe, for tax reasons or so, you have to have big computing pikes, right? Or you have a large workshop where many people try out your products, a demo session for your game, right? So, and suddenly you need much, much more computing. Instead of putting this in your own cellar, right, in the company, this is just a period of maybe 1 month. It doesn't make sense to do this just for Christmas shopping of your customers and say, well, after this Christmas, my load on all of these different services will go significantly down. So the elasticity enabled the cloud to say, you can always have more resources or less, depending on what you need. Of course, you swipe the credit card for it, or you save money if you take less services, but it's available. And this on a basically click basis. We will learn in Amazon and in Google and MS Azure how this is actually true. It's very simple these days to create this so-called EC2 instances that you see here, which are then, of course, leverage also many of the others that are existing in the Amazon Web Services cloud, like, for instance, storage. You see here the S3 stands for storage interface. We come to that later in the second part. Now, also the types of computing is, of course, a very important factor. The EC2s would be giving you the possibility to have multi-core CPUs, but also many core GPUs. And the same is also true in all other cloud vendors. So we have to talk a little bit about now what are these differences, right? So you cannot leave a cloud computing course without knowing a multi-core CPU and many core GPU. So in one respect, I hope it is already part of Computer Science 101. So everybody who starts in computer science should at least know that. Now, when we talk about multi-core CPUs, we have largely, lots of different chips, or let's say lots of different processors on one chip, right? And you basically have them with a very high clock frequency. They are really number crunchers, very good in computing and different cache hierarchies. But the trouble is you cannot get the clock frequency higher and higher and higher, because then basically it's getting too hot and you have more and more errors on the chip and so on in computing. So hence, this was giving us a limitation at some point in time that we cannot have just, thousands of multi-core, with high frequency. That is a problem that was basically coming up largely in the last 10 years, then solved with this technology called GPUs in a way. Solved not truly, because the problem remains that you cannot put just processors with high clock frequency again and again, more and more and more on the chip, up to the scale of GPUs. So hence, as the name suggests, here we have really not multiple processors, we have many, very many of these. And the reason why we can do is that we say each of the different clock frequency is basically lower. Basically, yeah, you heard correctly. So basically this is, moderate thread performance in all of these processors. The reasoning is that you can now, because the chip is not getting too hot, then put really thousands on a GPU chip. And this was sort of a breakthrough, really, to enable, again, computing at scale, because many of the problems where GPUs come from were basically much more an idea of a task-based or data parallel approach, right? Rather than this number crunching that we have in CPUs. You can remember, or some of you remember, that GPUs came from the graphic industry, And basically there, you know, they have sort of a vector approach. Many of the, let's say, visualization engine parts that we're using and leveraging GPUs are using the same paradigms, but just with different data. And basically in these days, many of the packages we have leverage GPUs as well. So again, you would still maybe need a CPU for it, but you connect them with main memory and device memory in order to get to the GPU and fuel it with data, come back to the host CPU. But there are also new elements where you can have a much more GPU to GPU interaction and so on. So for you here in the cloud course, that's the scale we're talking about. We're not going much more deeper like in the HPC course, but it's important to understand really the differences between those. Now, you can imagine that this is now the lowest ground that we discussed, the infrastructure as a service with the EC2 and then the storages. But what about developers, right, that now want to do something in the cloud and develop their own product? And, you know, here, for instance, Philips, we already talked about the Lightning approach, you know, basically at home Lightning. But you have also all the gaming industry now doing apps and so on, right? Angry Bird is something what we will discuss in the course and so on. And they need an engine. They need to know how to use a cloud at all. The Google Cloud is here just one example, but it nicely stands for the fact that you as a developer need a whole cycle, right? You need a software development kit here to build your apps, to test your apps and deploy it really in the cloud at scale, right? So upload, and then you start with thinking how many computing I need, how much data my app needs or my game needs for user data, but also for the game data. And then you basically upgrade this over time. So it's a cycle, right? So I have a new version, Angry Birds 2.0, whatever. And then, you know, you make it local development, of course, with, you know, tools, you know, but if you really want to test it and then give it, of course, at scale to the users, you put your service in the cloud. And the Google Cloud is quite nice with it. We will talk about in lecture 10 much more about it, why this is then considered as a platform as a service. Platform essentially standing for it gives you already lots of services you need, like for instance, a credit card component that, you know, you don't have to reinvent the wheel and program all of that, right? So if you want to have a game where people swipe their credit card, there are already modules, there are already elements like Lego bricks existing. The same is true for a bucket store, we will understand, right? And by doing these different services together, using essentially the cloud as a platform, you have really offerings like the Google Cloud Platform that helps you significantly and are perhaps a little bit oriented also to cloud developers and users, right? However, of course, we go into some details then in lecture 10, just to give you an appetizer. If you think about that, you know, Angry Birds was first a failure. They had a, you know, soccer game that didn't work really, the team, and then they started with Angry Birds, and this was suddenly a success, right? The business case you already all know. I don't have to talk much about it. I think everybody knows Angry Birds, but it has been quite an interesting story because it was growing rapidly. By now we have movies, we have lots of different franchises around it, but the scalability was kind of a really hard element in all of that. And without cloud computing, this would have never taken off, right? Basically, somehow 140 million downloads and users suddenly need to be catered in computing, right? If you as a company start then with a small server, you know, downstairs in your own cellar, as I would say, host your apps there, your data there, and whatever, you know, then you don't have any scalability that when overnight, or let's say in a week, millions of users suddenly want to download and play your game. I mean, you would be happy, more users, maybe more swiping the credit card, yes, but your server will significantly fail to deal with this load. Hence, you need this kind of infrastructure remotely, and we will talk about this, why this might be also better costs invested, right? Obviously, buying your own infrastructure costs, but also using it remotely costs. So there is a trade-off. But you will also see that the infrastructure is continuing remotely also to advance. New GPUs comes and your own infrastructure would be older, and et cetera, et cetera. So we talk about this a lot throughout the course. We also sometimes call that economics of scale, why cloud computing was really taking off. Then on the highest service layer, really, we talk then about Amazon Web Services here again as an example, just for the SAAS with a tool called SageMaker. We will also have in lecture 11 much more. This enables you really to train machine learning models at scale Again, fully managed, basically very easy to use, while it took a lot of efforts for you to do this in your own cellar if you have your own infrastructure created, because lots of software needs to be built on top in order to make this happen. And hence, the software as a service is a very attractive, let's say, way to bring software now to consumers, to people that actually use the service. And with this, basically coining really on this level, I think the major successes of cloud computing in a way, however, being built still on the successes of the infrastructure as a service and platform as a service models. Often we see them as a layered cake, right? So people use IAAS and PAAS services. But yeah, in a way, that was really all I wanted to bring you on the, lecture first, the overview lecture here. In the first part, where we talked much more about computing, we basically clarified, hopefully for you, some essential technologies, so many core, again, multi-core, but also the other technology elements like parallel distributed computing versus centralized computing, perhaps. So all of that basically enabled us to do cloud computing at scale together with all of these brilliant services. And this YouTube video here, I don't want to play it now, of course, but you can have that at home to see another perspective on cloud computing. So what is a cloud and so on from another one. So that gives you a fresh view on the subject. Hence, now after 10 minutes of break, I think we are ready for entering the second, let's say, area of the course, which is basically on big data and the scalability around it. So we break here for 10 minutes and see you then back.